Hello and welcome to the video on electric fields and electric potential. So the first thing we're going to talk about is electric fields, and an electric field is the space around any sort of electric charge, and there's a force field around that electric charge that interacts with other charges. So you can only observe these fields by watching the forces that it produces on these charges. You can't actually see an electric field, but you can see how the electric field affects things around it, and therefore you can observe the electric field that way. And these electric fields are sort of thought of as a storehouse of energy because we can use these electric fields to move stuff around if we choose to do so. But continuing on about electric fields, a couple things you need to know about them. One thing are the lines around the electric field. So you see we have charge A, charge B, and charge C at the bottom, and they'll have these arrows pointing out. These arrows are what represent the electric field. And a couple things you need to know. The stronger the field is, the more arrows that area has, and the closer the arrows are. So if you see a lot of arrows, then that's a really strong electric field. So you can see that charge C at the bottom is the strongest charge out of all three of these. Another thing you need to know, weaker fields have fewer lines, so that means the lines will be further apart. So more stuff about these lines that we draw. The length of the line indicates the amount of force. So the longer the line or the vector, that means that there's more force that is being applied from that charge. And also the direction of the arrows are very important. You see the charge on the left is a positive charge and the arrows go out. You're going to have to remember that. Positive charges, the arrows point out. Negative charges, the arrows point in. That's very important. You need to make sure to memorize positive charges point out, negative charges point in. So keep that in mind. Alright, so yeah, negative charges point towards the charge, positive charges point away from the charge. And whenever we put these two charges together, we're going to see how these interact with each other, and we'll get into that later. So, continuing on. Electric fields. As you can see, electric field A is just one positive charge, and all the arrows go out. Remember, positive charges, arrows point away. So looking at part B, you see that there's two charges next to each other, and these charges are interacting with each other. So, you see that the arrows are pointing out from the positive charge, and the arrows are pointing in from the negative charge, and you see that they are connected. So this sort of is a way to represent how these are attracting towards one another, like so, with my terrible arrows. But we can see that these charges are attracting each other. That's not the eraser. These charges are attracting towards each other, and that is one way that we represent the electric fields. So the positive charges are pointing out, and they're pointing towards the negative charges. So if we look at part C, we see that there are two parallel plates right next to each other. In part C, there's two parallel plates right next to each other. All the positive charges are pointing away from the positives, and the electric field is also pointing towards the negative. So you're going to have to remember that, become familiar with things such as that. Alright, so continuing on, part C shows the electric field that exists between a positively charged plate and a negatively charged plate. And you can see how the arrows are represented there. Electric shielding. This is something that we need to make sure we talk about, we're familiarized with, because it's very important as well. So whenever you look at any sort of conductor that's a surface like this sphere that we have over here on the left side, we see that all the charges are on the outside of the sphere. They're not like mixed up around the inside. So since all the charges are on the outside, they're being pushed away from each other. They're like repelling each other, and they're trying to get as far away from each other as they can, and by doing so they end up on the surface of the object. And so the electric field inside of that sphere is zero. There's absolutely no electric field inside of there. But if we continue on and we keep looking, we see that the car on the right is a good real-world explanation as to why this information would be good for you to know, because if you look on the right, you see a person inside the car, and the car is struck by lightning. But the person is safe on the inside of the car. That's because all the charges stay on the outside of the car. The car acts sort of like a sphere. It's not really a sphere, but it's like a metal box. And all those charges stay on the outside of the metal box. But if you look over here, though, the person that's outside of the box and they're touching the car, if they're actually touching the car at the time that the car gets struck by lightning, they're going to feel the all the electricity flow through them as if they were struck by lightning, because they're touching a conductor, and that conductor sends the electrical charge to the person. So electric shielding, all the charges stay on the outside. So if you're ever in a thunderstorm and you're in a car, make sure to stay in the car. Don't get out and try to do something weird. Just stay in the car. It's the safest place for you to be due to electric shielding. We also need to talk about electric potential energy. This is energy that a charge possesses because of its location. So there's a charge, and then where is it in relation to another charge, so we can figure out the electric potential energy there. So if you separate a positive charge from a negative charge, that increases the potential energy because you have to do work against their attraction. So remember when we were talking about potential energy before, if you go higher and higher and higher, you're getting more potential energy because you're adding energy to the system. So if you're spreading apart a positive and a negative charge, we know they want to come together towards each other, but if you spread that positive and negative charge further and further away from each other, you're adding energy to the system, and so you're creating potential energy, because we know what's going to happen once we release that positive and negative charge. They're going to come flying right into each other. All right, but same thing happens in reverse if you're pushing two like charges together. So let's say, for instance, I have a positive charge and a negative charge, and I'm trying to push them together. Or I'm sorry, let's back up. Let's say I have a positive charge and another positive charge, and I'm trying to push them together. What's going to happen is they're going to repel, because we know when charges are the same, they repel each other. They try to get away from each other. So if I'm pushing two positive charges together, the closer I get them together, the more potential energy they have, because they don't want to be there, and they're going to fly away from each other once I do that. So there's two ways to add potential energy to charges. If it's a positive and a negative, you push them further away, then they'll come together. But if they're the same charge, you push them together, they're going to want to fly away from each other. So that's two ways to add potential energy to charges. Continuing on, talking about electric potential energy, or just electric potential now. Electric potential energy per charge is sort of a way we're going to talk about it. But it's also known as potential difference. So if you hear potential difference, we're talking about electric potential. Also, the term you're probably most familiar with is voltage. So anytime we say the word voltage, that's also the same as potential difference, which is the same as electric potential. So if you hear me say any of those, I'm talking about the same thing. Okay? So just keep that in mind. And our units that we're going to use are volts, so be ready for that. And 1 volt is equal to 1 joule per coulomb. So you could either write your units as volts or joules per coulomb. So you can create a very large voltage, but if you only have a few charges, there's a very low potential energy there, because there's not many charges. So if we have a high voltage, that requires a large amount of energy only if there is also a large amount of charge that's involved. So 1 coulomb is a very large amount of charge. Alright, so let's talk about capacitors for a minute. Capacitors are found in just about every single piece of electronics that you use: your cell phones, your computers, your iPads, your printers, your car stereos. They're all over the place. These capacitors are everywhere, and they're very, very useful to us. And what they do is they store electrical energy. That's their main purpose. That's all they do. And what they are is they're made up of 2 metal plates, like so. And there's a wire over here and another wire over here. And all these electrons go down the wire, and then they're stored up on this end of the metal plate. And then sometimes they will discharge across. Sometimes there'll be some sort of connector that connects them, and then the electrical charges can end up flowing down the rest of the path. So the electrical charges end up building up over here, and then they will be transferred across here. Either they'll just arc across, or they will have some sort of conductor connecting them to that will allow them to flow across from one metal plate to the other. So a fully charged capacitor has the same amount of voltage as the battery does whenever it's reached its maximum charge, and it discharges, so it goes from one plate to the other when there's some sort of path provided between the two plates. One example is one of the old disposable cameras that people don't really buy too much anymore, but you had to hold down the button, let the flash charge, and then you could take a picture with flash. So you had to use that capacitor in the camera, in the disposable camera. So if you ever want to go buy a disposable camera, take it apart, you can see a capacitor. But be careful if you do that. Some more additional notes, you might want to write these in the side of your note packet. We need to talk about a test charge. Test charges are a small, very, very small charge that when placed inside of electric field, it has little to no effect of the electric field around it. It can't really alter it that much. And so what we'll do is we'll know that the test charge is either positive or negative. 9 times out of 10 it's a positive charge. And we place it where we know there's an electric field, and we see how that test charge reacts to the electric field, and we can see what direction there is, what direction the electric field is moving. So for example, in our picture that you see down here at the bottom, we have our positive test charge right here, and we had this electric field. Let's say we didn't know what the charges were, and we place a positive charge, let's say right here, and we see that it moves this way. Well, that means, we know like charges repel, so that means this has to be positive, and we know unlike charges attract, so if it's moving to the right, we know that this has to be negative. So that is one very useful thing to know about test charges and their information. They're very useful in the everyday world too, when we're trying to figure out how charges work and everything. More things you need to remember. Electric field, there's a way to calculate the magnitude of the electric field. How strong is the electric field? And what we do to do that is just the force divided by the test charge. So E is the magnitude or strength of the electric field, F is the force applied to the test charge, and Q is the test charge in coulombs. So how strong is the test charge? And our units for the strength of the electric field is newtons per coulomb. So if we look at our example problem down here, it says a charge of 0.0003 coulombs is used to test the electric field of a central charge of 6 coulombs that causes a force of 800 newtons. What is the magnitude of the electric field? So the first thing you need to do is you need to look through and figure out all the information that you need. So we know we're going to need to solve for E. Wow, my handwriting's great. And then we know what the force is. So the force is 800 newtons. And then we also know the charge of the test charge, which is 0.0003 coulombs. And this piece of information right here, this 6 coulombs, central charge of 6 coulombs, that's just extra information. We don't need to know that. So, just trying to confuse you. So we just plug it into our equation right here, right? E equals 800 newtons divided by 0.0003 coulombs. And you could put that in your calculator, and whenever you do put it in your calculator, you will see that the answer is 2.7 times 10 to the 6 newtons per coulomb. Whenever we work with these problems, you're going to have to be very familiar with scientific notation. It's so much easier to write out your answer like that with the times 10 to the whatever. That way you don't have to write out tons of numbers, and also your calculator will give you answers like that most of the time. So be familiar with that. Make sure you know how to work with scientific notation. Another equation that we can use to find the magnitude or the strength of the electric field, so this will find the same type of answer as the last slide did. It's just if we're given different pieces of information. For instance, if we're given voltage, such as potential difference, or if we're given the distance between the two charges, then then you'll need to use this equation right here. The electricity, or the strength of the electric field equals the voltage divided by the distance. So for example, we have a problem down here when an electron, right here, this is the charge of one electron, negative 1.6 times 10 to the negative 19 coulombs, moves 0.1 meters along the direction of an electric field with a strength of 3 newtons per coulomb. What is the magnitude of the potential difference, also known as voltage, between the electron's initial and final points? So this piece of information here about the electron, that's just extra information. You don't need to know it, because we know the strength of the electric field. It gives that to us right here with 3.0 newtons per coulomb. And then we are looking for the voltage, because that's the potential difference. The question is, what is the magnitude of the potential difference? And we know the distance, which is right here, 0.10 meters. And then we can plug that into our equation. So that's 3.0 newtons per coulomb equals V divided by 0.10 meters. Multiply both sides by 0.1. So that's 3.0. I'm going to drop the units just for now. 0.10 equals V. And you could do this in your head if you wanted. It's just 0.3. So 0.3, and then the units for potential difference is volts. So there you go. That's your answer for that problem, and hopefully you know something about electric fields and how to calculate the strength of the electric fields now.